Hey guys, I'm Pat Kelly. Okay, in this problem, they ask us to find the total mass of a spring, and then they give us some density function. Okay, so the rho function is given to you there, and also this vector r is given to you, and that's what defines the spring. Okay, we have to find the total mass of that. They've given us a little bit of a head start by just kind of reminding us that the formula for mass here is going to be to integrate over the path of the spring the density function, okay? But I also even took it a little bit further and broke it down. If you see the pink, what we're going to need in order to do specifically this ds part is the ds will be the magnitude of the derivative of the r vector, okay, and then dt. Okay, that's what you need to do whenever it's parametrically represented, so our t's everywhere. Okay, so I think I have a setup for success now in order to get into that formula, specifically the pink formula. Notice you do need that r prime. So a first step, almost always a good first step in a calculus problem, is to do a derivative. And what we're going to do is differentiate that r of t vector right above and get an r prime of t, which is just the derivative of your individual components. So minus 2 sine of t times the I vector plus 2 cosine of t j vector plus 1 times the k vector. Okay, that's good. Get some partial credit for your differentiation. Why did we do that though? In the formula, I need the magnitude of this. So my next step is let's find the magnitude of this r prime vector. And hopefully remember with magnitude, it's equal to the square root. And then you sum up the individual coordinates or components squared. So I look at the negative 2 sine of t and square it and get a positive 4 sine squared of t plus, and then I square the next component and I get a 4 cosine squared of t plus I square the next component, which is just 1, and all of that's under the square root. And this is always nice when this happens, that inside it simplifies quite a bit, because my sine squared plus cosine squared, you know, would be 1. There's a 4 in front of those, and then add the 1 that's trailing along, and we get a square root of 5. Okay, so that's going to be my magnitude component of the formula. So let's go down here and start working on that formula. This will get us our answer for mass. It equals, and I'm following that pink formula. You can see that it has the integral from a to b, which will be your t values, where you start and where you end, 0 to 4 pi. I did leave a little bit of a space, if you notice, only because I'm looking ahead. And what I need inside the integral is that rho function, and my rho, my density function, does start with that constant factor of a half. So I think I would have pulled that out in front of the integral. Okay, and then in order to actually utilize this rho function, first part is x squared, and x refers to the first component of your r vector. So I'm looking at minus 2, I'm looking at r prime, that's my green. Let me slip up to purple. X squared, you want to look at the first component of your r vector. So 2 cosine of t, I've got to square that and get 4 cosine squared of t. Then a plus, because that's what's in your density function, plus y squared, which is going to look to the second component of your r vector. So 2 sine of t, but squared. I'm going to get 4 sine squared of t. And then plus from the function z squared, and z is your third component of t, but squared. And I'm going to put parentheses around all of that. That's just my density function. I'm looking at the formula. I still need to multiply by the magnitude of the r prime vector, which was our square root of 5, and then dt. Okay, now we'll try to evaluate that integral. As I go down a step, I am going to pull out that factor, the constant factor of square root of 5. So let's write this as square root of 5 over 2 out front. Integral from 0 to 4 pi. Let's capitalize on that Pythagorean identity again, right? I see cosine squared plus sine squared, which is just 1. There is a 4 in front of that, so I would have 4 times 1 plus t squared. And then we're already at the dt, right? Integral doesn't look too bad. Let's evaluate it. Slide over if I do this. I still have the square root of 5 over 2. And then I'm just looking at antiderivatives for t plus t cubed over 3. And I need to evaluate that from 0 up to 4 pi. Plug and chug time. So this equals square root of 5 over 2. And then I'll use some parentheses here. Plugging in the 4 pi, I'm looking at 16 pi. And then plus, plugging in the 4 pi, 64 pi cubed. The pi is cubed, divided by the 3. And you gotta love the zeros here. That's just gonna subtract and then 0 when you plug that in, so that's nice. I think I'm good there. And I might clean it up just a little bit. If I factor out, I guess a 16 pi would come out nicely. Divide with the 2, and I'd be looking at 8 pi times the square root of 5. And if I pulled out a 16 pi, that's just a 1 inside plus 4 pi squared. It's cubed. I pulled one out, right? And then divide by 3 in parentheses. And that's our answer. That's the mass, total mass of this spring. Okay? Try some on your own, of course. I'm sure you'll do well.